Our first speaker is Amander Clark. Amander is a professor at UCLA, and she has been working all her life in stem cells and in vitro gametogenesis. She's a superstar in the field. She is involved in many, many projects working with human, monkeys, etc. On the top of this, she also has projects that are involved to how we can transmit the science into the real people and changing how we see the stem cells. On the top of that, she's incredibly supportive, and I've been one of the persons that got, in some point in my life, a letter of support from her. So we are really, really thankful to have her here today. And Amander.
Thank you, Miguel. I really appreciate the introduction, and I'm absolutely delighted to be here. This is my second Magee-Women's Health Research Summit. The first one that I went to was the very first one, and I found it to be transformative, the way that the summit was organized to bring together scientists, physicians, policymakers, thinkers. It really changed the way I started to think about my science as well. So I'm thrilled this is the third one, and I hope that there can be many more to come. Today I've titled my talk Stem Cells, Reproductive Health and Society. So I'm a stem cell scientist, and as Miguel said, I've spent my entire career utilizing stem cells in order to understand how they can be utilized to generate cell types and tissues of reproductive organs in order to improve reproductive health. So I wanted to begin with this slide to start a conversation about what is reproductive health. So reproductive health, as defined by the World Health Organization, is a complete state of physical, social, and emotional well-being in all processes and functions as it relates to the reproductive system. And all of us in this room utilize our reproductive system across the lifespan, which is why it's one of those very important systems that changes at birth, it changes at puberty, it changes during the reproductive years, and it changes in the post-reproductive years as well. And a reproductive health at each point in these parts of the lifespan, the needs are different, the health care is different, and the way it impacts our overall well-being is different. In the last 5 years, what has emerged, particularly in the United States, is this concept of reproductive justice, but it precedes the most recent election cycle. Reproductive justice was in fact born at around 1994 in the United States by women who felt that they were not being served by the women's rights movement, and particular in the way that the women's rights movement was not enabling them to have choices about their reproductive autonomy, the choice of the number and spacing of children in their family, and choices about sexuality. So the reproductive justice movement and the reproductive health have come together over recent years, in particular in the United States, in order to develop strategies to improve access to care for those individuals who are not receiving reproductive care that's consistent with what their needs are. Most notably, we talked yesterday in our session about reproductive healthcare deserts that exist over the United States, and how access to care for the people who live in these deserts is absolutely crucial for their health and well-being. So reproductive justice and reproductive health are often thought of as the tip of the spear in the delivery of access and care today. But what about reproductive science? Where does science fit into this? Because science isn't immediate. It's not something that can happen with a grant in 1 year time. All of a sudden you're changing care within the next year. This is a long road and a long process. And as a consequence, reproductive science has fallen out of the national conversation around reproductive health. And I believe that reproductive science should be back into the national conversation, just as science is the foundation for healthcare that impacts all of us and all of the different parts of our lives, as we discovered during COVID. Reproductive science is absolutely essential to moving healthcare forward with reproductive health and also in the framework of reproductive justice. So I've put reproductive science here because reproductive science is the generation of knowledge in order to improve our understanding of the reproductive system and therefore to have a positive impact on reproductive health. Reproductive science also forms the foundation for reproductive justice because it's providing fact-based knowledge that informs the reproductive justice movement that also informs reproductive health. So I feel like this is the trifecta: reproductive justice, reproductive health, and reproductive science that needs to work together in order to work towards equity in reproductive health and care. So as Miguel said, I'm a stem cell scientist, and I started my career in stem cell science over 20 years ago, working with this structure here. This is a human blastocyst that's been consented to research, and these particular blastocysts that we're using when I started my lab at UCLA now just under 20 years ago, we were using them to derive embryonic stem cell lines. Embryonic stem cell lines were really important to the stem cell field because the promise of embryonic stem cell research was that these stem cells could form any cell type in the body. And by forming any cell type in the body, they could be used to replace cell types that have been damaged by disease or injury. So embryonic stem cells derived from human blastocysts donated to research originate from the green cells that you can see here in this blastocyst. The green cells are the pre-implantation epiblast cells of the inner cell mass, and embryonic stem cell lines are derived from the pre-implantation epiblast cells. So embryonic stem cells don't exist in an embryo. Embryonic stem cells are in vitro derivatives that are found within a tissue culture dish inside a laboratory, but they are derived from cells in the embryo, the pre-implantation cells. So embryonic stem cells were transformative to the field of regenerative medicine, and when I started my postdoc with Renee Rayopera, we were thinking about how could we use embryonic stem cells in order to create replacement cell types for those who suffer from reproductive disease or have been injured by a treatment that, for example, could destroy reproductive cells. So we started modeling the formation of the germline. But we knew that the use of embryonic stem cells was not going to be a therapy for infertility or for reproductive disease because these cells were not patient-specific. So the second transformative technology that occurred within the stem cell field was the derivation of induced pluripotent stem cells, which led to the creation of cell types that basically are equivalent to the embryonic stem cells that are derived from pre-implantation embryos. They're functionally equivalent in that they are capable of forming every cell type in the body, including the germline, as I'll show you. But what makes them special is that they can be derived from different people. So what that means is induced pluripotent stem cells provided the pathway towards personalized regenerative medicine with stem cell technology. And for labs like mine who study the germline and in vitro gametogenesis, this means that germline cells can be made in vitro from a person's own cells for those individuals who are looking for a therapy for their infertility due to loss of the germline or a non-functional germline. So in my lab, we study infertility, which is also referred to as involuntary childlessness. Infertility is a disease that affects 1 in 6 individuals around the world, as recently measured by the World Health Organization. It is a disease that knows no boundaries. It affects people with ovaries and people with testes similarly. Both males and females experience infertility. But what we do know is that the burden of infertility is unequal. And so, for example, women of African American descent suffer from infertility at 2 times the rate of non-Hispanic white women. We also know that Black women and Asian women are less likely to seek reproductive care, or the length of time between their reproductive care is longer than non-Hispanic white women, which is really important because all of us appreciate in this room that for women there is a clock on our reproductive system, that once the ovaries stop producing gametes, then the capacity to have a biologically related child is reduced to 0. So what are causes of infertility? So infertility is not caused by just one thing, it can be caused by multiple things. And that's because the reproductive system is complex and involves a lot of different organ systems in the body. So infertility can be caused by the inability to make a gamete, or the inability of gametes to fertilize, or the inability to make pre-implantation embryos, or the inability of those pre-implantation embryos to establish a pregnancy, and for that pregnancy to complete to term. Infertility can also be caused by injuries and diseases in the brain. There are glands in the brain, the hypothalamus and pituitary, which are absolutely necessary to the function of the reproductive organs. Infertility can be caused by problems with the reproductive tract, not just the ovaries and the testes, shown here are the ovaries, but it can be the fallopian tubes, the uterus, and as well as the cervix and parts of the vagina. Not all infertility is due to biological causes or injury. Infertility can also be due to the person who you love has the same sex gamete that you do. And so therefore, that type of infertility, called social infertility, is not compatible with the ability to have a biologically related child. So when a person is diagnosed with infertility, or if a same-sex couple wants to have a family, or at least one of those gametes is related to a partner in that family, then in vitro fertilization is required in order for that family to be built. In vitro fertilization itself is a transformative technology that has enabled millions of people around the world to start or to build their family. In fact, in 2021, the current statistics is that just over 2% of babies born in the United States are born as a consequence of in vitro fertilization. More than 200,000 cycles of IVF were performed in the United States in 2021 alone, and this is increasing year over year over year. So access and utilization of reproductive treatments is a therapy that's used by Americans and many people around the world to start and build their family. Science is used to improve IVF success rates, and this has also been really important innovations. Artificial intelligence and machine learning are currently being used today in the IVF clinic in order to pick that embryo that is predicted to have the most success rate in order to give the family or the individual the baby that they desire. Pre-implantation genetic testing, and there's different varieties of them, PGT-A, PGT-M, and PGT-SR, are used to be able to select for embryos. In particular, PGT monogenic disease is used to select for embryos that are not carriers of a monogenic disease when the parents are known carriers of a mutation. IVF leads to the creation of surplus embryos, and when a couple decides to donate them to research, then these are used by scientists to understand the basic biology of human embryos and develop different culture conditions in order to improve the culture of human embryos and the success rate of IVF. However, despite all of these technical innovations, cell culture innovations, IVF success rates remain stubbornly low, and they have remained low for years. One thing we appreciate is that the age of the patient, in particular the age of the woman, has a big impact on IVF success rate. If you're under the age of 35, your IVF success rate on your first round of IVF is around 50% on average. And then with each 5-year increment after that, the success rates go down. If you're born with fewer follicles in your ovary, which is called diminished ovarian reserve, then your success rates for IVF begin even lower. And so the curve is the same, but even at the age of 35, your success rate is around 30 to 35%. So given that IVF success rates remain stubbornly low, scientific advances are needed to improve reproductive care. So what are some of these new scientific advances on the horizon, and how are they worked with by scientists in the United States? So as it turns out, there is policy in the United States that is a barrier to reproductive scientists being able to develop therapies and cures for those individuals who suffer from infertility. The first one I'd like to highlight is the 1996 Dickey-Wicker Amendment. So this is a rider on the congressional budget, which basically means that agencies that are funded by Congress, which includes the NIH, NSF, as well as other organizations that give out federal funds, the rider states that none of these funds can be used for embryo research. And the NIH is and this Dickey-Wicker Amendment has a very, very specific definition of an embryo. The embryo here is not defined as an entity that's created by the process of fertilization. The embryo in the Dickey-Wicker Amendment is defined as any cell that has the potential, has organismal potential. So as it turns out, this rider on the budget, this rider that goes with the congressional budget, is very, very restrictive for what scientists can do in terms of understanding the biology of human embryos and utilizing stem cell-based embryo models in order to study human embryo biology. Another policy that is restrictive actually is in my state. It's in the state of California. And that was created through the California Institute for Regenerative Medicine. When that proposition was voted on by California voters, there was a line item in that proposition that said scientists can only culture embryos up to 12 days post-fertilization, which is 2 days earlier than the international consensus, which is 14 days, or formation of the primitive streak, whichever comes first, for the culture of human embryos. Once California voters voted on that proposition, that language was baked into the California Department of Public Health Code. And so therefore scientists in California can work with human embryos with California state funding, which is tremendous. But we have a barrier, and that's the 2-day barrier to be able to culture embryos further, to understand early embryo development, primitive streak formation, and peri-implantation stages. So scientists are trying to figure out ways to study human embryo biology in order to improve IVF outcomes. And so this has led to the creation of an entire suite of stem cell-based embryo models, which I find really exciting. These embryo models model the blastocyst stage of human embryo development, as well as the post-implantation stages of human embryo development. And you'll hear about some of this work today from Mo when he gives a talk a little bit later. There are tremendous ethical, legal, and social considerations for the use of embryo models. And this takes us back to that Dickey-Wicker Amendment. How similar are they to a human embryo? And do they have organismal potential? So this has led to a challenge with NIH knowing what embryo models can and cannot be funded because of the rider on the Dickey-Wicker Amendment. There's also questions about the moral status. The closer these stem cell-based embryo models get to a human embryo, then at what point do they have equivalency in terms of moral status to a human embryo that is created by fertilization? So there is a lot of questions right now in the international stem cell community about the applicability of existing embryo laws, not just in the United States, but around the world, to the use of embryo models in research. So given the challenges and the fast pace of this field, there's been a number of regulatory frameworks that have occurred in different parts of the world in order to create the regulatory space for scientists to be able to move forward, to be able to perform this type of science. Some of these regulatory frameworks are involving public engagement, and this is something that at the International Society for Stem Cell Research, we really endorse as a strategy for enabling the public to weigh in on the use of embryo models for understanding and improving IVF. So here are some examples of different guidelines as well as codes of practice that are being created around the world in order to create the framework and the space for working with stem cell models. What I want to talk with you about today, just for a little bit, is the science of in vitro gametogenesis. This is something that I began with when I was working with Renee Ray-Opera at UCSF during my postdoc, and continued in my own lab when I started at UCLA in 2006. And that is the science of in vitro gametogenesis. What that means is making germ cells outside of the body. So you can imagine there's somebody who has come into the in vitro fertilization clinic. They've gone through various rounds of IVF. They're at the 5th round and nothing's working. There's something is not right with those gametes or those embryos. So they're out of options. Their options moving forward are gamete donation or embryo donation or moving into adoption. What if you could make germ cells outside of the body in order to give that person the opportunity to be able to have the family that they choose? So in vitro gametogenesis might provide that in the future. But right now, in vitro gametogenesis is a research tool that can be used to improve in vitro fertilization, egg freezing, and egg recovery. There are tens of thousands of women in the United States today that are freezing eggs with the future promise of a family down the track. But we don't know the success rate of freezing eggs on this large scale. And eggs, we don't want to freeze and thaw eggs for research. So perhaps in vitro gametogenesis can be used as tools to understand and maximize the success rate of freezing eggs and thawing eggs in the laboratory. IVG could be used as a research tool to understand environmental impacts on reproductive health, also as a research tool for contraception discovery. That's how we're using it now. And in the future, it may be a solution to involuntary childlessness when IVF fails or is not possible. So how is in vitro gametogenesis conducted? It follows the principles of germ cell development from the beginning all the way through to the end. So the beginning of germ cell development is a journey that begins way back in the peri-implantation stage with the formation of primordial germ cells, which form at around the time of primitive streak formation in progenitor cells to the primitive streak and the amnion. Primordial germ cells then migrate through the embryo and then ultimately enter into an embryonic structure called the genital ridge, where the primordial germ cells will divide by incomplete cytokinesis, forming cysts. These primordial germ cells in cysts will get surrounded by pregranulosa cells, which is a cell type that's specific to the female ovary, and it'll support these germline cysts, and these germline cysts will enter a process of meiosis. So meiosis in the ovary occurs even before the baby is born. Sometime at the end, in the late second trimester, early third trimester, these germ cell nests and germ cell cysts will break down to form primordial follicles. These primordial follicles will ultimately form the ovarian reserve. Some of these primordial follicles, in fact, will activate during fetal life, and we're really interested in this activation process because this is going to dictate the number of primordial germ cells that are in the reserve at birth, which are those that are lost through follicle activation. And then ultimately, in the pubertal ovary, we have the formation of reproductive follicles. So that entire process needs to be modeled in vitro from stem cells. So before we can even do this, we need to understand how that ovary is built in the body using cell and molecular biology. So many, many years ago, I started the ovary project by working with Ian Glass at the University of Washington in Seattle, using human fetal tissue to be able to understand the earliest steps in human germ cell development. We were then joined by Brad Cairns at the University of Utah in order to map germline development and somatic cell development at a single cell level using 10x genomics. We started to apply some of this technology to non-human primates because there were gaps in development that we couldn't access with human fetal tissue, specification in the third trimester. So my lab started working with John Hennebold at Oregon National Primate Research Center to understand the spaces of development that we couldn't access in humans. We were then joined by Diana Laird at UCSF as we started to move into spatial transcriptomics and profiling of the human and non-human primate ovary. And then ultimately Jian Xu at Harvard University to be able to take all of this computational knowledge to build the framework for in vitro differentiation from stem cells. So this is a long and ongoing project over many years that we're hoping to continue into the future. So building an ovary in the lab is possible with mouse cells. It is not yet possible with human cells. So I'm just going to take you through a few slides of building an ovary entirely in vitro using mouse pluripotent stem cells and mouse cells. This is a process that takes around 40 days. It begins with pluripotent stem cells that are differentiated into a formative state of pluripotency called epiblast-like cells. This is equivalent to the post-implantation epiblast. These are differentiated as aggregates to make primordial germ cells, which are combined with the fetal ovarian somatic cells containing those pregranulosa cells, which when mixed together will self-assemble to form a small ovarian-like structure in the lab. This is what the ovary looks like in the lab when made from stem cells. So the germline here is made from iPS cells, which carries a blue reporter in it, so that's why they're glowing blue. So those are iPS-derived oocytes, and in gray are the ovarian somatic cells that you can see have self-assembled around these oocytes and are forming follicle structures. So these are activated follicles. But the mixing of the granulosa cells and the germ cells together doesn't lead to this immediately. There is still a developmental process that's occurring in order to build these ovaries in the lab. What they do is they begin with the formation of those germline cysts, those primordial germline cysts, which hopefully you can see here in green, that are forming within these little ovarian structures. And we can see this at day 4 after combining the germ cells with the ovarian somatic cells. These germline cysts will then start to assemble into these germ cell cysts in nests. And we can see these nests because they're outlined by laminin, which is marked here in the pink. And in blue, what you can see is the FOXL2 positive granulosa cells, which are intermingling with these cysts of germline cells that are found within the nests of the developing organ-like structure, the organoid. Within these cysts, the germline cells will enter into meiosis, and what we can see is very clear Pachytene stage meiosis within these germline cysts. And so we're very interested in studying this Pachytene entrance into meiosis and Pachytene within the in vitro oocytes, because we believe this is actually a big bottleneck in the technology, is accurately going through meiosis. These germline cysts will start to break down at around day 10, and we can see the liberation of germline cells out of these nests, and these germline cells will start to form follicles. Within the next week, as the nests break down, these follicles will start to form, and so what you can appreciate here is these oocytes derived from iPS cells that are now surrounded by these FOXL2 positive granulosa cells, and these FOXL2 positive granulosa cells have a cuboidal shape, so they've immediately started to activate. So what scientists are trying to work on is how do we get the granulosa cells to not activate, but instead to form the quiescent granulosa cells that form the quiescent ovarian reserve. And you can appreciate that these are now surrounded by a laminin basement membrane. Starting from day 10, when those nests break down and those follicles start to form, what we can see is this tremendous increase in oocyte growth. So these oocytes go from just under 20 microns to around 55 microns in diameter. 55 microns, as we know, is not competent for fertilization. In the mouse, we actually need it to go another 15 microns further before it becomes competent for meiosis. So what is necessary then for these oocytes, the cytoplasmic components of these oocytes, to increase in size in order to gain competency? And that's a really important area of investigation. My lab has also been working on how can we start to think about this organoid in the lab, the ovarian organoid, as a system that responds to other systems in the body, the endocrine system. So we started to develop approaches where we supply the ovarian organoid with pituitary signals, in particular follicle-stimulating hormone, to see if we can induce these ovaries to start producing sex hormones, so we can understand the biology of sex hormone generation in the ovary. And in doing this, what we were able to show by culturing it for another 10 days in culture using follicle-stimulating hormone and giving a little bit more germline support, GDF9 and BMP15, we can get a further increase in oocyte size to around 65 microns. We have 10 more microns to go for competency. But what we were able to show within these organoids is that they are now able to produce the sex hormones produced normally by an ovary, progesterone, estrogen, and testosterone, indicating that these ovarian organoids can be used for functional studies. So what I've shown you is that it's possible to make oocytes in the lab and ovaries in the lab entirely in vitro. And this opens up, you can imagine, limitless possibilities to understand ovarian biology entirely in the lab, to understand environmental impacts on the ovary by simply adding some of these environmental toxicants to these cultures and then asking what happens to the ovary and ovarian cells. It's really, I think has the potential to transform ovarian research. But how do we translate this knowledge to human cells? How do we go from the mouse, which is what I just showed you, to human? So we've been working on this in the lab for a long time as academic scientists, and now there are companies that are starting to emerge that are commercializing this technology to take it to the clinic. So what we decided to do is, as we've been working on this technology in the lab for using it for biomedical research purposes, we now need to start thinking about public engagement. How do you talk about in vitro gametogenesis to the public? Does the public even want in vitro gametogenesis? Is making germ cells outside the laboratory even something that society thinks is necessary? So what we decided to do at UCLA, and we did this with the Center for Reproductive Science, Health and Education, and scientists and researchers within it, is to perform a social science study by inviting stakeholders who would be utilizers of in vitro gametogenesis, that's people who suffer from infertility, to come in and talk in focus groups about the technology of in vitro gametogenesis. So this was a study that was conducted by philosophers Anne Le Goff, Robin Jeffries, and mentored by Hannah Landecker, who's a philosopher and historian at UCLA. And so this work was recently just published, and what it highlighted is actually some really rich information about public opinion on reproductive technology, rich information on public opinion about embryos and utilizing embryos in research, generating embryos for research purposes, but also their hopes as well as their concerns for in vitro gametogenesis. And I've just highlighted here some of the key statements from this paper. And so what some of the highlights are that they hoped IVG would provide gametes in a non-invasive manner. So this idea of women receiving hormone injections to stimulate their ovaries is a real concern for women who are suffering from in vitro gametogenesis. And they can see in vitro gametogenesis as a way of no longer needing these invasive hormonal injections to retrieve oocytes. Our LGBTQ plus respondents voiced hope that IVG could support inclusion and equity in family building. And I have members of my team that are identify as LGBTQ plus and gender fluid, and they work in my lab because they have hope that this technology could be available for them one day in the future. Respondents had concerns on IVG safety, as I do too. IVG should never be used for clinical uses until it's proven safe and effective in preclinical models. And so what my concern is, as IVG is being talked about in the public sphere, that it might be available in 5 years' time or 10 years' time. And in terms of the pathway to the clinic, that's just not a realistic timeline. So I'm excited about the commercialization of in vitro gametogenesis and its wide applicability to the public, but it's really, really important that we're very truthful about how science moves and how the pace of science moves, but also what is needed for in vitro gametogenesis to make it to the clinic, and what is needed is proof of safety. So with that, what I've talked to you about today is that pluripotent stem cells have opened new avenues of investigation into reproductive science and women's health, that using induced pluripotent stem cells creates opportunities to increase inclusivity in science. And what I mean by that is when we started working with embryonic stem cells and when we looked at the ancestry of all the embryonic stem cell lines we were deriving at UCLA and around the world, they were basically derived from people of Caucasian ancestry. So what that means is that there's a large section of the human population that is not included in this research. So induced pluripotent stem cells enables us, with informed consent, to derive induced pluripotent stem cells from those people who want to be included in research from across the different spectrums of ancestry that make up the human population today. I do want to leave you with, given the ethical, legal, and social implications of research and implications of the research that we do in reproductive science, public engagement is absolutely critical for any type of value-laden science, of which the reproductive sciences are, to be able to move towards translation with public trust. So with that, I'd like to thank you very much.